Okay. Let me know if it hops up here. Should be live on my channel. Okay. Okay. There we go. Cool. All right. Everyone hear me okay from this? We're up? Okay. Hello, folks. And hello, YouTube. I'm live on YouTube right now, in case you're curious. So just Google my name, you'll find it. Or you can just watch in person. Less lag that way, right? So it's good to see you all. I am Christian Hubicki. Hopefully you're all in the machine learning class here. Oh, actually, I gotta. So part of the technical setup, you might notice a bunch of rat's nest of cables going around. That's the way we're recording everything. It's streaming to the internet. It'll be available as a VOD afterwards. So what could go wrong, right? Except everything went wrong this morning. All right, so we're all here for machine learning, right? Great, awesome. This is Machine Learning Introduction and Applications. I am Christian Hubicki. I'm your instructor. This is 4930, 5930, 0009. It's both undergrad and grad class. So it's good to have you all here. And so we meet Tuesdays and Thursdays at this time slot, okay? There's no textbook purchase required. But there are textbooks for the class. But the good news is they are free and online, okay? We're specifically, I'll go over on another slide the different textbooks we will mostly go out of. But what we will be going mostly out of is the Goodfellow text on deep learning. Anyway, office hours, we're going to figure out our office hours. And we have 2 TAs for this class. We have Nicholas Gearhan, if you could wave your hand right there. That's Nick Gearhan. And Jacob Hackett in the back there, right? Those are your 2 TAs for the class. It is a packed house here. I'm not nervous. Okay. All right. So, all right. The course schedule will be posted on Canvas. We're still getting the Canvas page online. Right now, all that's up there is the syllabus on the files page, which I'll go over the relevant details today. Additionally, so who am I? I'm Christian Hubicki. Hello. Okay. I am an associate professor of mechanical engineering here at the College of Engineering. My specialty is in robotics. So I will use some robotics examples, but this is not a robotics class. This is not a controls class. This is a machine learning class. And what that means, we will talk about today. See, look at that smile. Look, we talked about this, right? Yes. So right here at the Joint College of Engineering, I am aware, who here are mechanical engineers by degree? Anyone who's not a mechanical engineer by degree path? Really, I'd heard rumors that people, I thought, okay, well, welcome everybody. So that's good for me to know. So also I have hobbies. Sometimes I'm on an island. Google it if you're curious. Anyway, ask me a question. So yeah, if you're curious why your professor was in Entertainment Weekly yesterday, Google it. Okay, so the syllabus is posted on our Canvas site. So there are 3 key components to the grading for this class, okay? One, there are online quizzes. They're approximately bi-weekly, but they're basically whatever I think we need them, all right? And they'll likely be on Canvas, okay? And in addition to that, oh, sorry, I got to start recording this thing here as well. So many buttons to push. Why to make this so complicated? All right, so online quizzes. No time limit, open book, open note, okay? The point is to make sure that you are following the course material, okay? Because that's very important, because while there's a lot of flexibility in how you tackle the class, you don't want to fall behind, okay? That is my major piece of advice. Keep up on the lecture materials, etc., and the quizzes help you do that. Notice that homework is 40% of your grade, okay? That's because that's where you do most of the actual work yourself. There are going to be mostly coding assignments, okay? So there's going to be a lot of coding in this class. Now, do you need to be a coding expert? Absolutely not. You can be new to coding. We will do lots of coding examples to help you along, okay? So you don't need to be an expert. We'll talk about what you need to know going in. But you just got to commit to wanting to learn. That's what I want from you guys. And additionally, we have a final group project, okay? You get to choose your groups. You get to choose your project, all right? Talk about that in a bit. So there are no traditional quizzes as in like, pop quiz. Here's a paper in front of you sort of thing. There's none of that. No traditional exams nor a final exam, okay, for this class. Very much a learning class. Please learning class. Code on your time to try to get your homework and projects done, okay? This is a higher level course. This is a senior level elective and a grad course. So really, you got to be on top of your own time, and as I would expect from any successful students such as yourselves. So, okay? So, let's see if I can move forward. So, the textbook, okay. The main textbook we will be following is called Deep Learning by Ian Goodfellow and Bengio and Corville, okay? You literally just Google Deep Learning Goodfellow. It'll take you to the website. It's free PDF. I'll tell you, it's a good textbook. I rarely just go straight out of a textbook in terms of course material, in terms of order. It's really great. I was literally, for reasons that some of you may know, I spent some time alone this summer. And there was a period of time where I brought with me Deep Learning by Goodfellow. And I was reading it, and I'm like, if I wrote a textbook about machine learning, I would write it in this order, in this way. It's really, I really like it. Also, Reinforcement Learning and Introduction is what it's called, by Richard Sutton and Bartow. Okay, we'll cover a little bit from that, and various online papers and text. But you do not have to buy a textbook. So if you want to get ahead on the reading, I really recommend diving into the first few chapters of Deep Learning. It's surprisingly accessible, at least I thought it was. So, okay, this is a hybrid course. A little bit of the course structure here. So we are face-to-face today. I see your faces, as we established prior, right? So I see your faces, you see my faces, right? On Tuesdays, we will see each other's faces here, okay? I will drag my streaming setup here so you can all follow, so that way we're live streaming here, okay? And we'll cover mostly lecture material. On Thursdays, we're on Zoom. Again, I'll be streaming, I'll be recording, okay? But you participate remotely. Why? Because I want you all in a comfortable environment with your computers, and you will be coding. We will be coding along with each other, okay? So there are a lot of things we'll be coding from scratch. So if we're doing a gradient descent algorithm, guess what we're doing? We're going on Google Colab, pulling up Python, and we're writing line by line the code. I will, shockingly, sometimes make mistakes, and we will fix them live, okay? So you're not only learning how to code these algorithms, but also the process of debugging them, okay? And I think it's really valuable. After each of the lectures, there is a video. I love apparently I'm on camera a lot, okay? So I record these things for your benefit. I also post the code online and the lecture notes that we take live online. So that way you have the material after the fact, okay? So we will be coding in Python for this course. A little bit more on that later. I know that none of you have, by requirement, had to use Python as part of your mechanical engineering materials. I don't think. There's not a required course that requires you to use Python, right? That is okay. I am aware of that. Who here has used MATLAB? That's what I hope to see. Almost everyone, right? Structurally, it's not that different from MATLAB, okay? But and my other course that I offer in the morning, Applied Optimal Control, is in MATLAB, okay? A lot of the tools that we use for optimal control are really well suited for MATLAB. But in order to train you for the field at large of machine learning, a lot of the tools are Python-based, okay? So if you've never coded in Python before, that is okay. We're going to get you up to speed, okay? Will be some learning? Absolutely, okay? Don't expect it to be easy, but I hope that it'll be rewarding, and we'll try to make it as fun as possible. So more on that later. But so we'll be using Python, and a lot of the great packages for machine learning, and particularly deep learning, are in Python. So we'll be using that. Particularly Google Colab, we will use an online interface wherever possible. If you have your own way of executing Python via VS Code or other things, if you're familiar, by all means, you're more than welcome to do that, okay? So prerequisites for this course. You might have noticed the prerequisites were a bit vague on the website, okay? That is, I'm sure, so just to add some clarity here, these are the things that I really want to make sure people know, because I try to make sure the course is as accessible as possible. I don't try to put strict, like you have to have taken linear algebra to take this course, because linear algebra is not required for your curriculum, right? Okay? But you don't have to take an entire course in linear algebra to function in machine learning. But prerequisites. Calculus. Can you take a derivative? That's what I really mean. Okay? If you need a reminder, you look scared of that. That's sarcastic, right? You're good. I assumed you're fine. What's your name? Maya is fine with taking derivatives. You're ready to take a derivative right now, right? I assume this much, right? So really, really, we need you to take derivatives. That's what we want. You do need to be able to do a really complicated integral by parts and do a Riemann sum. We won't be doing that as much in this class. That's the thing we'll be using. Linear algebra. What I mean, can you multiply a matrix with another matrix? You know, there's lots of great subject to linear algebra. And to be clear, there's so much of machine learning that uses very interesting and deep linear algebra, right? But to get you going as an introduction and application, this is the level of linear algebra I want you to be familiar with. If you haven't multiplied a matrix since algebra 2, just look it up on Wikipedia. There's a great tutorial, okay? Remind yourself, all right? So number 3 for coding, okay? Can you write a loop and assign variables? That's the kind of coding we're looking for. Can you plot something? You plot the things that you would do in MATLAB for all your other courses, right? I don't expect you to come in and it's like, actually, I have very strong opinions on functional programming schemes. Sorry, I'm subtweeting my TA over there. Does he have an opinion? Sorry. Anyway, sorry, you do what you're doing. I'm sorry. So you don't have to be a strong software engineering background. You didn't have to intern at Google over the summer or anything. We will walk you through how to do these things with loops, okay? So now, yes, we will be covering object-oriented programming. Who here has done object-oriented programming at all? A couple of you. You probably have, but you didn't realize it, to be honest. So, but we will walk through those things, okay? Because some of these tools that people use for more advanced machine learning, they give you a toolbox, and they say like neural net dot learn or something, okay? That little dot and do something, that's object-oriented programming. And that makes it really simple, right? You know, like, oh, this thing, dot, that thing. That's a super, super high-level take on object-oriented programming. Okay, policies for the class, okay? I'd like you to attend, okay? And that is for, frankly, your benefit. Because what happens is I think people will come in, they're excited, a lot of people are excited for the class, and you're like, yeah, but I'd rather work on my other homework assignment. I'll catch the VOD later, the video on demand later. And then people really fall behind is what happens. So I really, all I ask for you guys is that you're here. I'm not giving you in-class exams, okay? There is an excused absence policy on the syllabus. I also have what is called a research deadline extension policy, okay? Anyone here do research at all? There's more than like 3 of you. I know, yeah, okay. But if you do any kind of research, or if you have like some kind of, or you work for some laboratory or some other professor or something, there are deadlines that are inflexible. We have them in my lab, believe me. And if one of those things is coming up and you're like, I really need an extra week on the homework, great. Just have your research advisor, CC your research advisor, and they say, yes, that's all I need, okay? And then I'll give you an extension, right? Okay. I don't copy each other's work. Don't make me go into that direction, okay? Don't make me play detective on whether or not someone's copied each other's work. You can work together. Work through problems together. Like, oh my goodness, my code is not working. Jeanette, what do you think the problem is? Well, I think it's that. Well, thanks, Jeanette. That's great. That's awesome, right? Okay, but you don't take Jeanette. Jeanette, can I take your 3 functions and just copy them and put in my thing? Don't do that. Okay. Don't make me play detective and find out who copied whose work, because I've done it. It was kind of fun, but I don't want to do it again. Makeup assignments. I can't guarantee any makeup assignments. I can't guarantee late homework, like credit for late work. Really, this is my pitch that when I drop a homework assignment, get started. Okay. It might be like, oh, it's due 2 weeks from now. That's plenty of time, unless you are a whiz at this stuff. And even then, I really recommend starting early, because then you get as many opportunities as possible to see us at office hours. I don't want to have to do the situation where I've done many times where I get panicked emails from a lot of students and I'm like, okay, I will have Zoom office hours at 8 p.m. at night right after dinner, and I'm in my pajamas. Why am I in pajamas at 8 p.m.? Okay, I promise no pajamas. But like for my Zoom session online, right? I mean, I don't want to have to do that, right? So starting early gives you the most opportunities to help debug your code, okay? So really recommend that. And so all the lectures we posted on Canvas in video form, right? I mean, literally, if you go on the YouTube channel right now, is anyone on the YouTube channel right now? You are. Is it working? You actually hear me?
Yeah, really well.
We worked really hard on this. So anyway, so okay. And if there is late credit assigned, I will do a blanket thing across the board, but I don't want to be in that position. Okay. Again, homework 40% of your grade. It's coding based. Again, just start early, okay? One other thing is that we'll be very specific about the format that we want the homework submitted. It's almost going to be code and like reports of what the output of the code is. If you don't follow the format, it makes things really hard for the TAs to grade. Okay, so we're going to be pretty strict about saying, look, you didn't follow the format, we're going to ding you points, okay? And that's free, following the format. That doesn't require knowing anything about machine learning. So free points. Think of it that way. It's like a deal. All right. Yeah, don't copy. Specified format. All right. So Canvas quizzes, they're on Canvas. They are not timed. They are open book, open note. Just make sure you can answer the questions right. Okay? So no exams, no final. But there's a group project that's due at various points throughout the semester, various checkpoints, but it's due at the end of finals week. It said final exam day. It's actually, so anyway, details. So you get to apply machine learning techniques to a project of your choice. Oh, goody. Anything you want, okay? Some interesting problems, some interesting application. If you have a senior design project that requires machine learning, you're like, Dr. Hubicki, can I apply to that? Yes. I have a research project that is machine learning. I want to apply machine learning to my research project for Professor X or whatever. Can I do that? Yes. I want you applying what you learn in this class to stuff that's useful to you. Absolutely. Okay? There are 4 components. Early on in the semester, we'll form groups. You can form these groups yourself. If you need, you put in a proposal which has some ideas, a draft, which is later on, make sure you have some basic elements of it together. And by the end of finals week, you got to submit a final report and a final presentation about your project, and we'll have it recorded as a video to submit. I would love for all of you to present to everybody else. I've done this in the past. I bring donuts. There are too many of you. Okay? So just submit. You're going to submit us a video of you all doing the presentation. Okay? Grad students. So how many of you are taking this for grad credit? Oh boy. Okay. So for grad credit, the difference for grad students versus undergrad credit is the homework will have more complicated components to do. Okay? And you have more requirements on what you do as on the project. Like you are basically responsible for your own like machine learning algorithm or application that you're applying to this problem, right? If you're an undergrad, you can work with someone else and like, okay, the 2 of us, we put together this unsupervised blah, 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 blah. You can do that. And to the point where if you tell me you're a grad student, it's like, actually, I have this project, I want to do it alone, just tell me so we can talk about it to make sure you're not taking on too much. That's fine. Okay? All right? I can do exceptions on group sizes. That's fine. All right.
Professor?
Yes?
So just to clarify, if we're a grad student, we're allowed to work in like groups of 2?
Correct. You are still allowed to, yes, as a grad student, you're still allowed to work in groups, but let's say you're doing the same project. Like I am predicting the turbulence model of some aircraft, okay? Well, you might apply, I'm going to do a multi-layer perceptron. It's like, well, I'm going to see what, and the other grad student's like, I'm going to see what I can do with this model, right?
Okay.
Yeah, so you need different approaches to the same thing.
Okay. And then do grad students have to work with other grad students? Like you don't want them crossed between like undergrad and grad?
I will allow student mixing between grad students and undergrad students. I didn't mean that phrase is weird. Sorry. You are allowed to pair up between undergrads and grad students.
Okay.
That is allowed. Okay. We would just, at the proposal phase, have an agreement as to what we required for each. Make sense? Mm-hmm. Yes. Thanks, Angela. Any other questions? Okay. All right. Oh, sorry. The fun part. So, coding, we are coding in Python for the reasons that I stated. Who here has coded in Python before? Oh, wow, that's actually a fair number. Okay, and that is, again, not required. Helpful, I'm sure, but not required, okay? For all the reasons, and the thing is, it's actually pretty easy to pick up. It's an interpreted language as opposed to a compiled language. Who here has taken a course in C++? I think it's required for like all y'all, right? What did you have to do before you could run your code in C++? Anyone know? It rhymes with schmumpile. Compile. You have to compile your code, and it gives you the errors, and you run the executable, the blah, 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 blah. In interpreted language, you don't have to compile, right? You just run the script top to bottom. So it's a pretty easy language to pick up. Now, one of the benefits of a compiled language is that it will run faster at the end of the day, and there's other advantages as well. But Python's easy to pick up. That's why people who were creating machine learning code spent so much time creating a nice, easy interface for using machine learning code so more people could use it. So, but those of you who haven't used Python before are like, oh my goodness, how am I going to keep up? How am I going to do all these advanced machine learning algorithms with Python if I've never coded Python before? Well, in part, there are packages we'll talk about in a second that make things easier, but also we're going to have an introductory, call it recitation okay, for people who want to have more experience with Python, where I will asynchronously code up with you all. We'll go through a project of coding up a game called Gorilla, okay? Now, the graphics will not be quite as advanced as this, you know. Think of all the GPUs you have to run. Like, yeah, you got it, all right? This is a game from 1990 that I learned about when I was a wee baby. So basically, you get two gorillas. They're throwing bananas at each other, okay? And they take turns choosing a speed and velocity to throw a banana, and then throws it back, okay? And what you'll learn if you're newer to coding is that we will tackle it in stages. You know, you won't even necessarily have an animation, but can we draw a trajectory of a banana that's flying at each other, okay? So the exact structure, so we're gonna figure out exactly when I'm gonna do the introduction to Python. We'll have a coding introduction to Python that you can join at the same time, or you can watch it remote. You can watch it asynchronously after. But really, it's designed for people to make sure they feel comfortable using the basics of Python. And the things that we'll do for this game, you know, writing loops, creating vectors, and stuff like that are the exact same things that you use for our machine learning algorithms. Okay. All right. And there are deep learning packages that are based out of Python that people have written for Python that are super handy and like basically industry standards, things like PyTorch and TensorFlow. Right now, our TAs and I are trying to work on the later assignments for the class to figure out which of these two packages we'll use. But we'll use one of them in order to make it easier to do the deep learning elements of the course later. Okay. All right. With that, so in terms of like what object-oriented programming is like, you can see where it says like nn.linear, nn.relu or ReLU, right? This is basically, that's an object where nn is an object, and it allows this little dot notation. It allows you to call functions within it. Anyway, we'll talk about that later. I just want to show you that's what kind of the code looks like, okay? All right, any questions about the structure of the course so far? Everyone's perfectly understanding. No one's intimidated. Glad to see it. All right, so let's talk a bit about, I guess, me, why I'm here. Okay, this is my first time running a machine learning course. And I've always felt, and I'm glad we're doing it, because I always felt that machine learning is a big enough topic that each department should have their own kind of specialized introduction, because you all, as mechanical engineers, have very different background than people over in the computer science department, or the scientific community department, or the ECE department, or the civil engineering department, right? You have different background, okay? What is my background? My background is robotics, okay? I work in legged robots. This is what I did during my PhD in postdoc, robots that jump, robots that walk, robots that run, did some analysis of ostriches, all that sort of thing. And in the lab, just right down the hall, is SysCore, our Center for Intelligent Systems Control and Robotics. We have humanoid robots like this one. I specialize in humanoid robotics. You can find I put up some videos on YouTube of me talking about humanoid robots. I have to stay on top of it, which means I spend a lot of time on YouTube these days because there's so many YouTube videos of cool robots. But this is our robot Digit walking over an obstacle, balancing itself dynamically, making all these calculations. And a question that you'll often get when you do this is people ask you, is it AI? Is it AI? The answer, technically, is yes. It is AI. But what do people think when I say that? They think it's going to want to kill John Connor. You know, it's self-aware. Okay. But here's the thing. Is it AI? Yes. Is it using machine learning? No. It's not using machine learning. What? How do these things make sense? Well, there's a lot of confusion about the terms AI and machine learning, okay? And they can be, so this is from the Goodfellow text. They put together this diagram, this Euler diagram, which is a fancy word for a Venn diagram, okay? Look, the outermost circle there is AI. It's lots of things, okay? It's basically any kind of algorithm that does things that humans would normally do as a task, okay? So even things like that you wouldn't consider that smart, like your thermostat, is AI. It's making decisions. Is my house too cold? If yes, turn on the heater. Is it not too cold? Turn off the heater. AI. So in a lot of ways, it's AI. But but inside of AI, that little bubble in the middle is machine learning, okay? This is a bit of a more complicated diagram than I like to put together. So I made my own diagram, which is better because it has colors, okay? And it's a little bit more relevant to what people talk about AI today. So if someone came up to you in your life, anybody here would volunteer, if they tell you, what is AI, what would you say to them before I just told you the answer, I guess? Anybody? When someone says, oh, that's an AI video, what do they mean? Nobody? No, you're all completely unaware of these things. Okay. Yes?
If someone asked if like a video is AI, I would just say it's not generated by like a human.
Yeah.
Like, it has no human interaction to like making the decisions to like create it.
Yeah, so it's like it's a video that's been generated, sort of a fake video, right? That's what we mean by AI. Like AI, it's using a very specific set of tools. I'm sure no one here has heard of ChatGPT, right? That's what I assume. It's a completely foreign concept to students, as I understand it, right? So that's what people mean by AI as well. You give it a prompt and it gives you all kinds of stuff. Now Dr. Hubicki's soapbox on ChatGPT is that it's amazing what it can do. You got to be careful about what it can reliably do. Okay. People have heard of hallucinations. Anyway, we're not at that part of the lecture here, but I feel like you got to address the elephant in the room that AI is a big deal these days. Like I saw an article that said it gets more press than God. I'm like, that might be true. Like just in terms of like how many articles about religion are there versus AI? There might be more on AI. It's a huge industry. Okay, the computer chips that are very good at training these AI models, they're called GPUs. Who knows what a GPU is? Anybody? Okay, you raised your hand about half in the back. We sort of did this. Is that a yes? Okay, what does that mean? What is a GPU?
A GPU is effectively what's creating the image on your display.
Yes. Like a GPU is a graphics processing unit. It's the reason that you can display all these pixels on a screen. Okay, back in my day, you'd buy them because just because you wanted better video games to play, right? Right. Nowadays, it's a $4 trillion company. NVIDIA is worth $4 trillion. That's more than I got on me. Okay? Because people figured out that these big AI models that they train, they're really easy to train on these graphics processing units. We talk a little bit more about why later, but that's pretty good. Wish I was in on that. That's pretty neat, right? Okay, back to the point that I was making that I completely forgot. So we go back to here. We're talking about blah 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 blah. This. All right. So AI is the big bubble on the outside. Lots of things are AI. Okay, but not all of AI is machine learning. Machine learning is when you take in data and then you change what we call a model based upon that data. For instance, that is incredibly general, right? So one example we'll talk about, who here has used Excel in their lives? Okay, yes, you're right. Has anyone done a scatter plot of points? Has anyone done a trend line through it? Congratulations, you've done machine learning, okay? Because that algorithm, which is incredibly simple, takes in all those data points and says, here's the best trend line to go through it. It takes in that data, it adjusts its model, which is the trend line, okay, and says, here, it's updated based upon the data. Machine learning. It's so simple, right? But that is machine learning. Now, the reasons that you're hearing about quote-unquote AI more and more these days is because of the progression to these more and more complicated and intricate methods, okay? For instance, deep learning, okay? We've known, and specifically what we call artificial neural networks. Who here has heard of neural networks before in their lives? Yes, I imagine most of you have, right? We've known about neural networks and how to set up neural networks for many, many decades, okay? It's only become big in the last 12 years as a real big boom for deep learning is that people figured out how to train those models, okay? We've known you can make big models, that's great, but how do you get them to do anything useful? Well, one of the things people figured out, there's a famous paper on something called AlexNet, where basically they trained a neural network to identify images. And this is a long-standing problem people have been working on. But what this particular paper figured out was that if you use multiple GPUs, those graphics cards for games, you can actually take in a ton of data, a big amount of data. One would call it big data. Anyone heard that term? Right? Big data, big data. And all of a sudden, the reliability of this thing skyrocketed. It became so much better at classifying, like, that's a cat. That's a pencil in that image. That basically didn't exist before the 2010s in any reliable way, okay? And then you have what are called foundation models. Who here's heard of foundation models? That is okay. But you have heard of examples. ChatGPT is a foundation model. If you've heard the phrase large language model, a large anything model, that's a foundation model, okay? That's the fancy word for it. So if you want to sound cool to your friends, you're like, oh, I'm really excited about what's happening with foundation models these days. I'm like, well, what's a foundation model? So, well, everyone knows ChatGPT, that's a foundation model, right? Then you have to find a new friend because they don't like you anymore. So, all right, so that is the big advent for in the 2020s, that basically foundation models allow you to take in data from a massive set of different types of tasks, and it's a much more general purpose algorithm, okay, that you can put together, okay, a much more general purpose model that you can put together. That's the progression of AI, machine learning, deep learning, foundation models, okay? Now I'll give you some examples just from my own wheelhouse, so to speak, of legged robotics, okay? So this is a robot from a company called Boston Dynamics. Has anyone heard of Boston Dynamics? Okay, very famous robotics company. They've been making fantastic robots for like 25 years almost these days. Okay, look at this robot. It's jumping, it's doing parkour, incredible. Look at, I put in the little corner where it is on that little Euler diagram. It's AI, it's making decisions on the fly. It's doing things that a human would normally kind of do, right? But it's not using machine learning, at least the control part is not really using machine learning. I can't speak to the vision part. That's a completely different thing. I'm just talking about the control side, okay? That's where I specialize. But it's not doing things like the deep learning, all the stuff you're hearing about, right, on AI, right? Fantastic, right? That's 2021, 4 years later, which is the blink of an eye in a field of study. This is their next version of Atlas. It's sleeker, it's more efficient. It's picking up parts, putting them in bins. They jumped all the way, they're using foundation models now to make it do that, right? Funny how things change. So something on the outside that I don't know how different this looks in terms of the technology is a fundamentally different approach, okay? So I just want to give you all an impression as to what the scope of these different types of machine learning algorithms are like, particularly in the conversation about legged robotic control, just something I know a lot about. So, and here's another example. This is the Unitree G1 doing, look at this. Boom, 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 boom. Pretty cool. This is amazing. This is just last year, and this is already well out of date. It's incredible. Like they're doing even cooler stuff now. And this is using deep learning, but not a foundation model. We don't know for sure because they don't release what they're doing, but everyone knows that it's using deep learning, but not a foundation model, right? So these things have different uses for different applications, okay? So let's keep moving forward. So again, so here is that diagram. So was my robot AI? Yes, but it wasn't using machine learning, okay? So if you come into class, you'd be like, hey, I'm going to AI class with Dr. Hubicki today. It's like, well, that is technically true because machine learning is a part of AI, but it's a machine learning class because AI is even broader than machine learning. Does that make sense? Makes sense. Okay, that makes one of us. Great. All right, so applications of machine learning. I was putting together this lecture, and I'm like, okay, what applications do I highlight? And I gave up. I just said everything. Like literally every field. I have a hard time thinking of a field that has not been touched by machine learning in terms of a research field or application. Image recognition. Is it a cat? Or it's like now who has like a photo app where you can search for what's in your photos, right? Like, oh, I want a picture of Steve. Like, oh, there's Steve. Or like, I want cats. Oh, there's cats, right? That's machine learning, okay? Studies, if you want to study like the effects of rainfall on different crop outlets, that's machine learning. It might not even that complicated machine learning. It's just everywhere. So if you're having a hard time thinking of a project, broaden your thinking, okay? Anyway, so that is the big picture on applications of machine learning, okay? Now let's talk a little bit, any questions before I move on to a bit more of like a traditional writing on a piece of paper sort of lecture? Anybody? Ooh, writing on paper, how exciting, okay. All right, so, okay, and there we go. 2026, oh, that's crazy. Is it the 8th? Thank you. I was on leave last term. Time is a flat circle to me. All right, so machine learning. An introduction. Machine learning is a statistical process of updating a model with data to perform a task. Okay? One thing you'll encounter in the field of machine learning is this term over and over again, model, 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 okay? And model means so many different things to so many different fields, it's crazy. And so because now machine learning touches so many fields, it actually creates things, it makes things a little annoying for people when we want to try to use the word model. Like, but the reason that these things are called, so the thing that you get at the end of a machine learning process is a model, okay? And the idea is that you get some input that goes into a model, okay? And that output should solve some kind of task. And a lot of times it's a prediction, like is this image a cat, okay? Or a dog. Actually, in the early days of deep learning, there was a fun little test that I think it's well out of date now. Could it determine the difference between a Chihuahua and a blueberry muffin? If you zoom in on a Chihuahua's face enough, it looks like a blueberry muffin. Anyway, fun fact. So I think that problem is pretty well solved at this point. But anyway, so is it a Chihuahua? Is it a blueberry muffin? It's a prediction. It's an output. Okay. All right. So, but the term model, the reason it's called a model is because it comes from the world of statistics. When people talk about statistical models. Okay. So, all right. So you have some input. You have a model, and this model is trained on data. Okay? Now, the classic example that I always bring up is linear regression, the trend line in Excel, right? So you have some input X, some output Y. Oh my goodness, all these data points. Okay? And you draw a trend line, okay? All these little data points here, I mean, that's the data. This line here, y hat equals mx plus b hat, okay? That's your model, okay? Where your input would be your x. You would say, hey, if I have a good model, and I say, I should be able to ask it, hey, here's x hat. Here's my prediction as to where things, what value would my model predict should be for y? And the answer is right there, right? And that would be a y hat, okay? Right? So, and the training of the model, what's its job to find? We already, we would be asked x, and we have to tell it y. What's left? M and b, okay? This m and this b, these are free parameters. Okay? Now, there are lots of ways to go about finding M and B. There is one best one that Excel uses and every algorithm uses, but we'll probably try a few just to get you in code, just to get you used to how this works, okay? But machine learning is all about finding that M and B. Are some M and Bs going to be better than others at fitting the data? Yes. Yes. Oh, no. That's incorrect. All right. So yes, it's going to be finding the right M and B, right? So when you look at machine learning in this very simple example, hopefully it becomes clear what machine learning is doing. It's about finding the M and B. But here there's only 2 parameters. For a big neural network, there could be millions or billions, right? So for that, you need a lot more data, hence why people call it big data, okay? But that's what the advent is finding what those parameters are, okay? So there are 4 key components to any machine learning approach, okay? If you're trying to define a machine learning approach, okay, you're trying to take data to perform a task, you need to know 4 things, as a general outline, okay? 1, you need to know what your data is. What kind of data are you looking at? Okay. 2, you want to know what your model is. In this case, this is a linear model. It's y equals mx plus b. It's a line. Okay? The 3rd thing you need to know is something called your cost function. People who took my machine learning, my optimal controls class this morning saw this concept of a cost function. Okay? But it tells you what is a good model. Is this model good or bad? Okay? What's good, what's bad? Okay? And the 4th thing you need is some kind of optimization algorithm. Nick, we still good on the screen? This is what's used to train your model. To find the best cost that you can. Okay? So a cost function, so anyway, so a cost function defines the goodness, quote unquote, to use a technical term. It's not a technical term, that's a joke, to be clear. Okay? The goodness of a model. Okay? All right? And higher is bad. It's a cost. We don't like to play in costs, unless you're some kind of masochist, right? So less is good. So lower is better. Lower cost is better. So let's take this linear regression example. We have in front of us 2 of the 4 components for a machine learning algorithm that we use in order to make this model. Okay? We have the data, meticulously drawn by yours truly. Okay? You have the model. I just told you, hey, it's going to be a line. Who gets to choose that model, though? You do. I guess in this case I do. But normally you do, right? You have to make that choice. And there are good choices and bad choices about models. Okay? This time I chose an easy one. People have seen in Excel you can do all the quadratic regression, the logistic regression. When you're doing that, you're choosing a different what? Model, right? Okay. Now those can all be trained extremely simply, okay, using linear algebra approaches, linear algebra-based approaches, okay. But we have not defined yet the cost function, okay. And in this case, what would be a good cost function? Well, we want the line to be close to the data, right? That's a simple way of putting it, but there are good and bad ways to define it, okay? So a cost function, let's talk about a cost function. All right, good. We still have an hour left in lecture. That's good. So a cost function, okay, is going to be a function of your model. So you have to somehow define your model in terms of variables, okay? And we're going to call these variables, for the purposes of this particular lecture, there are different ways to report it, I'm going to call it the variable W, okay? All right? Where the W is a list of potentially many, many parameters, such as M and B, okay? So we'll call them, for instance, W1 or W2 up to Wn. And I'll put them in these little brackets here. Anyone know what that's called? It's a vector. You didn't make me have to do a stupid rhyme to tell you. Look at that. Thank you. It's a vector, right? This is a vector of parameters. Those taking my optimal controls class will see some similarities to these representations because there's a lot of similarities across fields here. Okay? All right? It's a vector of parameters, right? So this cost function, f of w, is going to return a single value. What's a single value? When a vector is a single value, it changes to a different name. Scalar, right? So we call this a scalar valued function because it returns a scalar value. Okay. I'm making machine learning sound like baby stuff, I think, which I guess is a good thing. Okay, all right. So this is what we call a scalar valued function. Okay. Right? It's got to return one number, right? So for this linear model, for this example, for this, what we want is what's called a least squares regression. Well, the idea is that if you have your model y equals mx plus b, right? These are your two parameters. That's your w1. That's your w2. Okay. And you say your cost function. Let's make it this. We want it to be good across all the data points, right? So if one data point's bad, that contributes to the cost, right? You add them all. You'll add up a whole bunch of little costs, one for each data point. So it'll be the sum across all the data points. I'll be a little sloppy with the math just for today. So where you would say that across all of your data points from 1 to capital N, okay, it is the difference between the data point yi. So yes, question.
Does it matter if f of x here changed from f of w, or is f of w just like a standard like catch-all?
It changed to f of w because Dr. Hubicki made a mistake.
Okay.
Thank you. Thank you very much, Anne. One-handed clap. Thank you. To f of w. Thank you. Okay. And this we're going to call w1, and this we'll call w2. Okay. So the difference between the actual data point yi and we're going to put little hats here on the prediction here, y hat, x hat for a prediction. Okay. We want the difference between the data point and the model to be as small as possible, right? So let's compute that difference. Minus y hat. Now, we're going to try to minimize f of w, right? Right? So what's a good way to minimize f of w here? Well, you're one step ahead of me. If I wrote this like this, I've created a catastrophic error because the way to minimize that is to make yi minus y hat extremely negative, right? So what's a way to prevent something from going negative? Someone just told me. Square it, right? Right. Thank you, Angela. Right. So a least squares regression, right? That's what this comes from. Okay. And we would substitute in, y hat is equal to our m, which is w1 times x hat. But for a particular prediction, it's going to be at a data point xi plus b, which is your w2. Okay. So f of w is the sum from I equals 1 to n of yi minus w1 xi minus w2 squared. There's your cost function. Okay? It's a least squares regression. There are lots of different ways to write that simpler, okay, but I'll just be walking you through it in a very, very, I think, simple way. Least squares regression. All right. Now, the last thing you need is an optimization algorithm. It's the thing that finds the lowest cost model that it can find, okay? So a very common approach in machine learning is used to something called gradient descent. Someone finished my sentence, which is great. Okay, you'll hear this all the time. And when you get to deep learning, people use something called stochastic gradient descent, which means it's a bit more random. But the idea is that if you have this cost function, f of w, and w is your, let's just say there's just one parameter in this model. It's even simpler than what I have. If you theoretically know somehow there is some curve that says how much cost there is for different parameters, right? What's the what part of that curve do we want? The bottom part, because that's the least cost, right? Least cost. I'm so excited I'm writing terribly. Okay, right. Best cost. What is that? Least, whatever. Okay, least cost. Least cost, right? So, but you might not know beforehand what that is, because if you did, you wouldn't need an optimization algorithm, right? So what people will do is they will start with a guess of what the best one is. That guess will be wrong, okay? And they'll say, hey, this is the cost. And then you would say, hey, what's the cost at this guess? You plug it through the function, out comes that number. Boom, great. You don't know what the rest of that curve looks like. All you know is just that point. I'll draw it without the curve right here, right? Now, you have a choice. You could go in that direction and search, or go that direction and search. We know magically what the right answer is, go left. But let's say we didn't. How would we know which way to go? Well, if we took a tiny little step in one direction and saw that it went up, we should go in the other direction, right? Because we will notice that the gradient was going up. We want to descend the gradient, so let's take a step in that direction. And it gets us closer to the solution, right? Over and over and over again. It's called gradient descent. Okay? So you iteratively search in a loop. That's why you got to know loops. One step after the next, after the next, after the next, until you get to the bottom. Okay? Now, remember I said it's important to know derivatives? What's a gradient? It's a bunch of derivatives. Okay? All right. So gradient descent is a very common algorithm. We will be definitely coding it up. And all of these packages that we're talking about in Python will have different versions of gradient descent that are basically a dressed up version of this with different features, okay? All right? So, let's see, with the 5 minutes, we have like a little more than 5 minutes. Try to keep it less than 5. So, what we learned in the last decade or so are all kinds of good, important ways to be able to train algorithms with more than just one parameter, more than 2 parameters, millions, billions of parameters, okay? If you're doing gradient descent, it's important to know what the gradient is, right? So a lot of what, anyone heard of differentiable versus not differentiable functions? Remember that from calculus? How do you think we define our models, with differentiable or non-differentiable models? Differentiable models, you betcha. You betcha, or ones that, or at least ones where you can compute the derivative. Sometimes there are cusps, but you can always have a defined derivative in this particular approach, okay? But like, because knowing the derivative is so important. So there's a very common function that people use inside of machine learning models, particularly neural nets, something called the hyperbolic tangent. If you wondered what that was on your scientific calculator for, the tan h or the tan, Jacob, how do they pronounce tan h these days? Tanch? He's my guy who knows. Jake, Nick, do you know what they call it? Tanch? Yeah. Tanch. There's no S. It's silly. Anyway, but you can't call it tan. Anyway, but it looks like that. And that happens to approximate like, oh, I have a little bit, my input is over here. It's very small. It's off. Over here, it's on, and it's smooth in the middle. Nice and differentiable. Kind of like a neuron firing in a brain. Kinda being the operative word. In many ways it is not, okay? In many ways it is not. But an artificial neural network will have millions of parameters. Many of them will look like this. Some will have this. I kind of lied to you a little bit. They're not always fully differentiable, but you can always easily compute a derivative. one where it's flat and then it's up. It's called a rectified linear unit. We love fancy words in machine learning, otherwise called ReLU. ReLU. So there's lots of these. This is what was really important when we got to deep learning, was defining these things. So we ended up finding better ways to define our models so they're easy to train. We come up with better ways to train our models with lots and lots of data. Okay? And we have a pretty broad understanding of the different kinds of machine learning. We have a really a lot of different types of machine learning that have emerged out of this process. Okay, I don't think we have enough time to talk about unsupervised, supervised, and reinforcement learning. Actually, I do. So three. Well, just a little preview for next time. We will talk a little bit about supervised, unsupervised, and reinforcement learning. And where these all differ is the type of data that they are given and the ways they collect that data. Supervised learning has what we call labeled data. You have to give it data that says, here's a picture, and that is a cat. Okay? Here's a picture, that is a dog, right? Okay? Unsupervised, there are no labels. Okay? It's just a bunch of data, maybe on a plot. So for instance, it's like, what does that even look like? Well, let's just say you have, data x1, data x2. There's a bunch of data here. A bunch of data there. Anyone see any patterns called clusters? You'd say, oh, you're with the human brain, say, oh, that's a cluster, that's a cluster. None of those are labeled cat or dog, but you saw a pattern there. Now, reinforcement learning, I think, is cool because it's very, very related to optimal control, my other class. And the data that you get is from your model interacting with an environment, and the environment gives you back data. So it's like learning from experience, like training a dog. Here's a treat. You reinforce it when it does something good, and then it says, oh, that was a good thing, I'll do more of that. That's reinforcement learning. And that's been a huge thing in robotics, but not just robotics. Anyone heard of like fusion reactors? Yeah, people use, they're like all this plasma that's swirling around in a big toroid, but you have to contain it with a magnetic field that is controlled. How do you control that magnetic field? Well, they created a simulation of this whole process and used reinforcement learning and came up with a better way to control it. Pretty cool. I will leave it there. Thank you all so much for coming. Look forward to have a good semester. Take care.